So, hello my dear, welcome to IMS Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, faculty, Department of Mechanical Engineering. So my dear, we will come in front of you with the excellent practice question, okay? So really this is the very excellent question and it might be approximately the same thing you supposed to be asked in the upcoming GATE examination. Okay, beta. So today's the question related to the topic is for the topic is entropy balance. So we have already covered the numericals on the problem on the energy balance. So likewise there is an entropy balance. So what is the question here? We'll start with that. Consider a steady heat transfer. The heat transfer is steady. Okay. Consider a steady heat transfer. A steady heat transfer, that means what is the change within the system? If you take this system, this is a wall. So this system is a steady system. This system is a steady system. That means there is no property will change within the system. There is no any property will change within the system. Okay. Now, what is that? Through a 5 meter to across 7 meter. That means the dimension it is given 5 and 7 meter bricks wall, house of the thickness 30 centimeter. So this bricks thickness it is given how much? 30 centimeter it is given. Okay. Now one day when the temperature of the outdoor, that means this is your outdoor, this is your outdoor. So this is your outdoor and this temperature have a 0 degree centigrade. How much? 0 degree centigrade. Okay. Now the house is maintained 27 degrees centigrade. So this is your house, let's suppose, and this house maintain 27 degree centigrade. Okay, 27 degrees centigrade. The temperature of the inner and outer face of the bricks, outer surface of the bricks wall is to be measured. That means this is inner. So at this point, at this surface, measure temperature 20 degree centigrade, and the outdoor, outside wall temperature, it is this outside wall temperature. This is all outside wall temperature is 5 degrees centigrade, and this is your inside temperature maintain 20 degrees centigrade. Okay. Now the temperature of the inner and outer surface, okay, and the rate of heat transfer through the wall. That means what is the rate of heat transfer? Q it is given through the wall is 1035 watt. Okay. So what you have to determine the rate of entropy generation in the wall, very important, where it is in the wall, and the rate of total entropy generation associated with this heat transfer. That means if there is a heat transfer, so what is the entropy generation within the system? Entropy generation in the wall, that means wall is as a system. So within the wall, what is the entropy generation? And also the total entropy generation associated with this heat transfer, total entropy generation. So we have to find S generation of the wall and S generation total. We have to find these two things, we have to find it. Okay. So just read the question, I will come. Okay, so this is the problem. Now we have to solve this problem. Okay, beta. How we have to solve? Please see this. Please see this. We have to solve this problem, and really this is a very good problem, beta. We'll solve this problem. We'll solve this problem. Okay. How to solve? Please see. So what is that, beta? This is your wall. So there is a wall, it is, this is your wall, okay. So this is your wall, great. This is your wall, and this wall have a this face and this face, and the distance between these two face is your 30 centimeter. That means this is your 30 centimeter. This is your 30 centimeter. This wall, it is your 30 centimeter. 30 centimeter. This is wall, and this wall. So see, my dear, this wall, this is your inside and this is your outside. So inside temperature, this is your inside and this is your outside. So inside wall temperature, it is given, I think it is a 20 degrees centigrade. So this inside wall temperature, it is your 20 degrees centigrade, and outside wall temperature, it is given 5 degrees centigrade. Okay, and a part of this one, there is a this is your fluid is flowing. A part of this one, there is a fluid is flowing, and this fluid, let's suppose it is act as a surrounding which is at inside, and this is act as a surrounding which is at outside, and this fluid have a temperature, it is given. Okay, this fluid have a temperature, it is given. So this fluid temperature, so let's suppose this is your wall temperature left side, this is your wall temperature right side, and the outside temperature, it is given. How much it is given? That means if you have to take, this is your T infinite 2 outside, it is given 0 degree centigrade, and this is your T infinite 1, it is given, this is 2, and you take this is 1, no problem, and it is given 20, how much it is? 27 degrees centigrade. Okay, let's suppose this is your T1 temperature, wall temperature, and this is your T2 temperature. So my dear, this is our system. Okay, and the heat transfer, it is given. How much heat transfer? Heat transfer, it is given how much? 1035 watt. This heat will transfer. So if you talk about the heat transfer mechanism, so what is the temperature profile? What is the temperature profile? This is your 27 degree. So these all are 27, 27, 27, 27. So these are the 27. 1 second. So this is your 27, 27, 27, and it will temperature will drop. Okay. Now the temperature is linearly drop. Again, the temperature is drop, and the again goes. See, my dear, this is where the temperature effect is there now. That is called immediate surrounding. So this is your immediate surrounding. This is your immediate surrounding, where the temperature profile will there. After that, the gradation, there is no any temperature drop. After the before that, there is no any temperature drop. So let's suppose this is your 27. This is your 20, this is your 5, and this is your 0 degree. So there is 5 to 0 degree, there is a temperature gradient. There is 27 to 20 degree, the temperature gradient. So this is called immediate surrounding, and this is called immediate, and this is our system. So this is, if you take this all as a, if you take this as a system, this is called extended system. This is called extended system. Okay, this is called extended system. Extended system. Extended system. That means system plus immediate surrounding. What is the extended system? System. This is our system. Wall is our system, and this is our immediate surrounding, where the temperature if a gradient effect is there. So this is called system plus immediate surrounding is called extended system. So this is the concept of extended system. So what you have to find? To find what you have to find? To find entropy generation of the wall, number A, and number B, entropy generation, this is total due to heat transfer. Okay. So we have to finding this, we have to apply the entropy balance. So what is the entropy balance? Entropy balance, entropy balance for the wall, for the wall. What is that? Rate of entropy in minus rate of entropy exit plus rate of entropy generation is equal to ds by dt of a system. Now here, since the system is steady, in the question it is given steady system, that means ds by dt of a system is equal to 0. ds by dt of a system, it is equal to 0. That means this is your 0. So what is the equation? So S entropy in, rate of entropy in minus rate of entropy exit plus rate of entropy generation is equal to 0. Now my dear, this is the entropy transfer. This is the entropy transfer due to the mass heat. This is the entropy transfer, that means rate of entropy transfer. This is your rate of entropy transfer by heat and mass. This is your entropy transfer by heat and mass, and this is your rate of entropy generation. This is your rate of entropy generation. This is your rate of entropy generation. So this is your entropy balance. This is your entropy balance. Now, so there is no any mass transfer. Why? Because this is the bricks, solid surface it is there. So there is no any mass will transfer. That means the mass transfer, entropy transfer due to the mass is 0. Only the heat will transfer. Only the heat will transfer. Yes or not? Only the heat will transfer. This mechanism, only the heat will transfer. Okay. Only the heat will transfer. So only the heat will transfer. Heat will transfer. So due to this heat transfer, entropy will transfer. So what is the entropy heat in and what is the entropy out? So heat transfer divided by the temperature, and what is the temperature? Temperature of a boundary across the heat will transfer. So if we write Qi, so heat transfer divided by T, it is your in minus same heat out divided by T at exit plus, and if we take this temperature, what is this temperature? Temperature at inlet and temperature at exit. So this heat will enter at this point, let's suppose, and this point is exit. So at this point, what is the temperature? 20 degree. At this point, what is the temperature? 5 degree. We cannot put 0 degree and 27 degree. Mind it. Why? Because this is our system. This is our wall. So if this is our wall, so we have to find indirectly entropy generation of the wall is equal to 0. So if you find the entropy generation of the wall, so we have to take the temperature of the wall. Yes, 0. Very Vivek, very good beta, very good. Yes, 0. Very good Vivek, very good beta. So this is very important. If we take wall as a system, so in that condition, the temperature, it is the system boundary temperature. And what is the system boundary temperature? The system boundary temperature is 20 degrees centigrade at which the heat will cross, and system boundary temperature at which the heat will exit at 5 degrees centigrade. So this is a system boundary temperature. So what is the heat transfer here? The heat transfer, it is your, what is the heat? 1035 divided by what is the temperature at inlet? Temperature at inlet 20 plus 273. Very important. You have to always keep into Kelvin. 273. So this is in minus same heat is out. What is the heat out? 1035. And what is the temperature at that point? The temperature of this wall face is 5 degree. So 5 plus 273 plus entropy generation of the wall is equal to 0. Now you have to easily find what is the entropy generation of the wall. Solve it. If you solve it, you can easily find entropy generation of the wall. How much beta? Vivek, how much? Entropy generation of the wall. How much it is? Please reply in the comment box. How much it is? So the temperature is very important. Here the temperature is 5 degree and here the temperature is 20 degree. Why? Because the system is our wall. What is the value here? Vivek, what is the value here beta? Just tell me. What is the value? The value is 0.191 watt per Kelvin. So this is the entropy generation of the wall. This is the entropy generation of wall. Now the second question in that one, they says that the second question is that, just finish it. The second question is that, so determine the rate of entropy generation of the wall. It is okay. Now the rate of total entropy, so this is your total rate of total entropy generation associated with this heat transfer. Yes, 0.19, correct. 0.19, correct Vivek, correct. 0.19, correct. Now my dear, and now we have to find that this is the wall entropy. This is the entropy generation of the wall, within the wall. Now, what is the entropy generation due to this heat transfer? That means, if such type of question they are asking, so you have to find the total entropy generation. You have to find the total entropy generation. So this here entropy generation of the wall, so that the temperature is the wall. Now if we find the total entropy generation due to this heat transfer, in that case we must be put the temperature at the immediate extended system. So this is our extended system. So what is the extended system temperature? 0 degree and 27 degree. So the total, if you find the total entropy generation, in that total entropy generation, we have to put always the temperature of the surrounding. If you find the entropy generation of the system only, like a wall, we have to put always the temperature of the boundary. This is very important, I am telling you. So if you find, one second. So now the second part B, the part B it is, so in this case we have to take extended system. Extended system. So what is the extended system? Extended system is the system plus immediate surrounding, plus immediate surrounding. Immediate surrounding. Immediate surrounding. And what is the system here? System is your wall. Wall is your system. And immediate surrounding is a surrounding. What is the immediate surrounding? Is a kind of a surrounding which have a temperature gradient. which have a temperature gradient. See, from this near to the wall, the temperature is not 27, not 20. It is between 27 to 20, near the wall. Near the wall temperature is 5 degree and little bit nearer to the this surface is a 0 degree centigrade. So in this region there must be a temperature gradient. So where the temperature gradient exists, that is called extended system. That is called extended system. Okay. After that the temperature is same 0 degree. Before that the temperature is same 27 degree. So again we have to apply the entropy balance. So what is the entropy balance? We know that entropy in, rate of entropy in minus rate of entropy exit plus S rate of entropy generation is equal to 0. Why? Because system is steady. Now if we put here, what is the heat transfer here? 1035 divided by temperature. Let's suppose here we can write heat transfer divided by T at inlet minus heat transfer divided by T at exit plus, very important, entropy generation, and we have to find the entropy generation of a total. So for the total we have to put the temperature of the surrounding. This is your surrounding, very important. The temperature is the surrounding temperature. So what is the heat transfer? The heat transfer it is 1035, and what is the inlet? Matlab, when the heat will in, what is the temperature of the surrounding? That surrounding is 27 degrees centigrade plus 273 minus 1035. What is the temperature of the surrounding where the final heat will exit? That is 0 degrees. So 0 plus 273 plus entropy generation total. This is equal to 0. So what is the total entropy generation? Please tell me, beta. Entropy generation total. What is the entropy generation total? Please tell me. What is the entropy generation total? Please tell me. Please tell me. So what is the answer here? The answer is 0.341 watt per Kelvin. So this is the total entropy generation. This is the total entropy generation. Now my dear, there is some note point is there. Some note point is there. What is that? Please note down. Please note down. See, many teachers stop here, but after that there is one of the best concept. What is that? See dear. See this one. Now my dear, if we see total entropy generation is higher than the wall entropy generation. Yes or not? Yes. Total entropy generation is higher than the wall entropy generation. Now if you subtract the total entropy generation minus wall entropy generation, let's see what is this one. That means entropy generation total minus entropy generation of wall. What is this one? Please tell me how much the value? The value is 0.15 watt per Kelvin. Now my dear, please tell me what is this? What is this value? What physically this value tells? Yes. Now Vivek, please tell me what physically this tells? Please tell me. What physically this value tells? Please tell me, beta. Please tell me. What this value tells? Very important. What this value tells? What this value tells? Please tell me. Why this entropy will... So, this is a kind of entropy generation. First, sir, this is the kind of entropy generation. Yes, this is the kind of entropy generation. It is also entropy generation. But who is the responsible? The question is, who is generation? The question is, who is the responsible? Who is the responsible to generate this entropy? Our question is that. Who is the responsible to generate this entropy? Who is the responsible to generate this entropy? Okay, tell me. Who is the responsible to generate this total entropy? Who is the responsible to generate this total entropy? Or who is the responsible to generate this wall entropy? Please tell me. Please tell me. Who is the responsible to generate this wall entropy? Number first, who is the responsible to generate this total entropy? Number third, who is the responsible to this entropy generation? There are three things. This should be have a very clear. Why? Because at that point, in the gate question, many students get confused. I will tell you. My dear, this is the entropy generation in the wall. Why? Why this entropy will generate? Why? Because see, the heat will transfer. The heat will transfer through a finite temperature difference. That means there must be a temperature difference. 20 minus 5. 20 minus 5, that means 15. And 15 value is a very large value. That means this is the considerable value. That means this entropy generation is due to the finite temperature difference. Temperature के लिए flow direction. Okay. Okay. That one. I think you are saying this one. You are saying this one. Vivek, you are saying this one. Yes or not? Please tell me. You are saying this one. If you are saying this one, this is very good. You have a correct answer. This is, I think you are giving this region, this answer. Okay. So temperature gradient, flow direction. Temperature gradient. No. This is the responsible due to the air flow. See, my dear. This is due to the internal irreversibility. Yes. Okay, good. Now I will explain you. This is the entropy generation in the wall is due to the internal irreversibility. From where this internal irreversibility come? Due to the temperature difference. Due to the temperature difference. Now, who is the responsible to this total entropy generation? This total entropy generation, also there is a temperature difference. Also there is a temperature difference due to the heat transfer. But this entropy generation is due to the flow of air. Very good. This entropy generation is due to the immediate flow of air. Why? Because there is a hot air, there is a cold air. So this air will flow. Due to this air flow, this entropy will generate. This 0.15 entropy will generate. That means it represents the entropy generation in the air layer on both side of the wall. That means both side there is a wall. Okay? Correct, Vivek. Now, see this one. That means we can write like that कि sir entropy generation total is equal to entropy generation due to internal or first let's external plus entropy generation due to the internal. So total entropy generation is the external entropy generation plus internal entropy generation. This internal entropy generation is nothing, it is the entropy generation in the wall. So what is the external entropy generation? S generation due to the external is what? S generation total minus S generation of the wall. So this is what value? External entropy generation is what value? 0.15. So this is your 0.15 watt per Kelvin. So this external entropy generation is due to flow of air. It is correct? So that is the very important. So if someone asks you in this question, someone asks you, if I am a question setter, I will ask you not this thing, I will ask you determine the rate of entropy generation due to external irreversibility. Yeah, we can ask, I can ask you determine the entropy generation due to the flow of air. So there are two things, and that two things are the same things. That means determine the entropy generation, determine the external entropy generation, number first, or you can say that entropy generation due to the flow of air. So how to find? To find entropy generation within the wall and to find entropy generation total. Now you have to subtract the total minus entropy generation of wall, that is the entropy generation due to the external irreversibility, due to the flow of air. So this question is very important, I am telling you. Okay, this is very important. Now we have to take a next problem, that is the next problem. Okay, we have to take this problem. Please read this question carefully. Please read this question beta carefully. See, steam at 7 megapascal, 450 degrees centigrade, there is a steam, is throttled. What is the throttling? What is the throttling beta? Is throttled. What is that throttling? That means expansion. That means in this case we can reduce the pressure. With same enthalpy. What is the enthalpy at inlet? The same enthalpy at the exit. So is a valve to a pressure of 3 megapascal. That means it will throttle to 7 megapascal to 3 megapascal. That means pressure will reduce. During steady flow, the flow is a steady process. Determine the entropy generation during this process and check whether if it is increase in principle of entropy will satisfy it or not. That means we have to find the S generation, and if the S generation is greater than 0, that means there is a principle of increase in entropy. So they are asking find the entropy generation. See my dear, this is your pipe, and in the pipe there is a throttling valve is there. This throttling valve, the inlet pressure, if you take this throttled as a system, so this is your inlet of the throttle and this is your exit from the throttle. So inlet it is a 7 megapascal and temperature is 450 degrees centigrade. What is the exit pressure? 3 megapascal. And the condition it is given, so from the steam table it is given in the question at the pressure P1 and temperature T1. You have a pressure and temperature. So if you have a pressure and temperature, go from the steam table and find the enthalpy and entropy first. So if you have this enthalpy entropy, now how to find the second property? That means at a pressure P2 and at this enthalpy, corresponding to this enthalpy. Why? Because throttling is a isenthalpy. That means what is the enthalpy at 1 is the same as the enthalpy at 2. Inlet and exit. So P2 you have and second property H2 you have. Why H2 you have? Why? Because H2 is nothing, it is H2 is equal to H1. So from this one you have to find the entropy at point 2. So at this 2 location you have the entropy. That means at this point you have an entropy and at inlet you have the entropy and exit you have an entropy. So inlet exit you have, you can easily find, and in this case there is a mass flow. This is not a heat flow. Previously there is a heat transfer, but in this case there is a mass transfer only. There is no any heat transfer. Why? Because throttling we act as an adiabatic process. That means there is no heat transfer. So during the throttling, the heat transfer it is 0. Heat transfer it is 0. So this is not a entropy generation. This is the entropy. In this case, the entropy generation is not due to not a heat transfer. The entropy generation is due to the internal irreversibility. Why the internal irreversibility is there? Why? Because throttling is a highly irreversible process. Why? Because throttling is a device in which the flow restricted. The flow will restrict. That means there is a constraint to flow of the fluid. If there is a constraint to flow of the fluid, there must be if there is a there must be an internal irreversibility. That means internal irreversibility will increase the entropy, and that entropy increase is known as entropy generation. So how to find? See my dear. So in this case, let's solve. Let's solve. Let's solve. What is that? So this is our pipe is there. Let's suppose this is our pipe. This is our pipe. Okay. This is our pipe. Okay. This is our pipe. In this pipe, there is a throttling device. That means there is a throttling device. So this is throttling device. Let's suppose this is a throttling device. Okay. In this throttling device, this is throttling valve is there. This is your throttling valve is there. So this is your throttling device. This is the throttling device, and this is your valve is there. Okay. So this is throttling valve. Now, let's suppose this is our inlet section 1, and this is our exit section 2. And throttling is must be adiabatic, so there is no any heat transfer. Throttling is an adiabatic device. Now the condition it is given, this pressure P1 it is your 7 megapascal, corresponding the temperature it is your 450 degrees centigrade. Now this point you have a pressure P2 3 megapascal. Okay. Now to find entropy, rate of entropy generation due to this process. You have to find rate of entropy generation due to this process. Okay. Now, what is given? It is a steady flow device. Since steady flow device, this is your steady flow device. 1 second, beta. this is your steady flow device. So if there is a steady flow device, that means ds by dt of a control volume is equal to 0. There is no any property change. Okay. Now heat transfer, it is not heat transfer, it is also 0. So we have to entropy balance S in minus rate of entropy exit plus rate of entropy generation is equal to 0. Is equal to 0. So what is the rate of entropy in? So this rate of entropy in, that means this is a rate of entropy transfer, and during this is due to mass. This is due to the mass. No heat transfer is there. So if there is a mass is in, so there is a entropy in. If there is a mass is exit, so there is a entropy exit. So how to find? Mass is in. So mass in, so this is a mass in Mi, and this is a mass exit Me, and if this is a steady flow, Mi is equal to Me. That means same mass. That means mass rate of flow in into a small entropy I, rate of entropy, okay, minus m dot same exit S of exit plus S of generation, this is equal to 0. So what is the S generation? Rate of entropy generation, it is equal to M exit entropy minus inlet entropy. Okay. Now if you divide the mass is there, S rate of entropy generation divided by mass flow rate is equal to rate of entropy exit minus rate of entropy inlet. हाँ, S2 minus, not S2, हाँ, SI, हाँ, ठीक है, great Vivek, great. Now you have SE value. How much it is answer beta? Please tell me. S exit you have 7.0046. S inlet you have 6.6353. Put this value. That means 7.0076 minus S inlet 6.6353. What is this beta? This is your 0.3693 kilojoule per kg Kelvin. Now my dear, so this is your greater than 0, yes or not? This is your greater than 0. That means it satisfied the principle of increase in entropy. It satisfied the principle of increase of entropy. So here S generation, okay, S generation, rate of entropy generation, not mass basis, is equal to 0.3693 kilojoule per kg Kelvin. So this is a specific rate of entropy generation. Now this is greater than 0. Now why the entropy will generate? Why this is greater than 0? Why? Because due to unstrained expansion, that means expansion against low pressure. If any fluid will expand against low pressure, yes, 396, correct beta, 35, no, not 35, it is your 3693, okay, no problem, it is also right, 3.6 approximately, 3.6, you are right Vivek, you are right. So this is due to, why this entropy will increase? This is very important. Why the, see beta, why beta, see my dear, why? Because if you find the entropy balance, the cause of entropy generation is very important. So what is the cause of entropy generation? This is because of unstrained unstrained expansion. And what is the unstrained? That means expansion. That means flow of fluid into a flow of fluid into a low pressure zone. Low pressure zone. That is called unstrained. So due to this low pressure, due to the low pressure zone, that is called low pressure zone, this creates the irreversibility. Internal irreversibility. This is cause a internal irreversibility. So throttling is an highly irreversible process. So you have to keep in mind for the throttling, some point is there. During throttling, no heat transfer. During throttling, no work transfer. During throttling, enthalpy at inlet is approximately equal to enthalpy at exit. During throttling, entropy generation must be greater than 0. This point always should keep into mind. This is no heat generation, no work transfer, enthalpy inlet is equal to enthalpy exit, and also S generation is greater than 0. So that is called irreversible process. So throttling is an irreversible process. So it will satisfy the principle of increase in entropy. So what the question last says that, and check if the increase of entropy principle is satisfied or not. Yes, it will satisfy. Why? Because it will greater than 0. It will greater than 0. Now take the next problem. This is your next problem. Take this next problem. Take this next problem. Take this next problem, beta. So a 50 kg block of iron. So this is your iron block is there. This is your iron block is there. So 50 kg block of iron casting at 500 Kelvin. So this iron at a 500 Kelvin is thrown into a large lake. So there is a lake is there. That is a temperature of 285 Kelvin. So this lake at a temperature 285 Kelvin. Okay. The iron block is eventually reached a thermal equilibrium. That means if you put this iron block into the lake, they have to attain a equilibrium common temperature with the lake water, assuming the average specific heat is 0.45 kg of iron. That means this is a C of iron. Determine the entropy change of iron block. Determine the entropy change of the lake water, and determine the entropy change during the process. That means this have to find the entropy change during the process. That means this is indirectly called the total entropy change. And this entropy change of the iron block, it is a within the iron. What is the entropy change? Why? Because beta, if you throw this one, this temperature will change. The iron block temperature will change. So due to this temperature change, what is the entropy generation of the iron block? Now this iron will transfer the heat to the lake. Why? Because it will decrease. That means after the equilibrium will reach, what is the final temperature of the iron? What is the final temperature of the iron? Please tell me. What is the final temperature? Vivek, please tell me beta, what is the final temperature of the iron? What is the final temperature of the iron in this case? If the thermal equilibrium will attain, what is the final temperature of the iron? Please tell me. What is the final temperature of the iron? Please tell me, beta, what is the final temperature of the iron? The final temperature of the iron is equal to lake temperature. Why? Why? Because lake act as a reservoir. It is not a temperature will change. If its temperature will change, if this will transfer a heat, yes or not? That means this iron block transfer a heat. This iron block transfer a heat to the lake, CV in temperature in. CV. What are you asking? CV in temperature in. CV increase, temperature increase. No, it's not temperature will increase. See, this heat will transfer and this heat will transfer through a large lake. Through a large lake. So, if it is a large lake, its temperature doesn't change. But the heat will accept by the lake. So, what is the final temperature of this block? The final temperature of this block is 285. If this is a small, that means if you take this iron block into a tub of water, there is a pot and in which the iron will take. So, from that one, you have to find the energy balance. What is the heat loss is equal to heat gain, and you have to find the common temperature. But it in this case, lake as a reservoir, it have a very large quantity of water. It have a very large value of heat storage capacity. So, it's have a large value of heat storage capacity. So, what the heat will release by the iron, the temperature of the lake doesn't change. So, the final temperature of the iron is equal to 285 Kelvin. 285 Kelvin. Okay. So, we have to find it. So, we have to find what you have to find? To find delta S of iron. Okay. Number first. Number second, delta S of lake water. Delta S of lake water, and you have to find, and also entropy generation. So, entropy generation during the process, that means S generation. This is a total. Is what? Is what? Okay. Take C of the iron. C of the iron, it is your 0.455 kilojoule per kg Kelvin. Yes or not? Temperature of the iron block after reaching the same temperature with the lake. Yes, temperature of the iron block after reaching the same temperature with the lake. Yes. Equilibrium temperature. Why? Because lake is a very high thermal storage capacity. So, what is the temperature final? So, the initial temperature of the iron, see. So, in this case, we have to always find the final temperature of the iron block. That means, to find final temperature of iron block. So, if you find the final temperature of the iron block, what is the reason? Since lake act as a thermal reservoir. Lake act as a thermal reservoir. So its temperature never change. Its temperature never change. That means, hence, final temperature, that means equilibrium temperature, of iron block T2 is equal to 287, T2 is equal to 285. So, you can find this value according to these questions. Okay. Now, is the time, it is approximately, it is ended. So, we have not able to finish it, but you can find the solution. I give you the solution of this one. So the iron block, 1 second beta, what is the answer it is there? What is the answer we have to just, so the iron block, that answer is minus 12.65 kilojoule per Kelvin. Entropy change of the lake beta, it is your 16.97 kilojoule per Kelvin, and entropy generation, it is your 4.32 kilojoule per Kelvin. So I hope you enjoyed this video. There are many more questions beta Vivek, but it is very sorry that the time is very constant. It is approximately 1 hour. So if you solve this problem, post in the comment box. If you're not able to solve, we'll meet again the next session. Okay, I hope you like this one. Thank you beta, thank you, bye bye.